Welcome to SSR Pharma Media, your trusted source for pharma knowledge. Pharmaceutical Inorganic Chemistry and Pharmaceutical Analysis MCQ series, your exam power boost. So, in Pharmaceutical Inorganic Chemistry and Pharmaceutical Analysis, so there is the topic Complexometric Titrations. Today we are going to discuss Prepare, Practice, Succeed. So, in Complexometric Titrations, we are going to cover what introduction about complexometric titration, classification of complexometric titration, metal ion indicators, it's also PM indicator, masking and demasking agents, preparation and standardization of disodium ADTA, estimation of magnesium sulfate and calcium gluconate. So, in complexometry introduction and principle. So, the complexometry principle is based on the reaction between metal ion and complexing or chelating agent. So, usually EDTA is used as a chelating agent. So, EDTA means diethylene diamine tetraacetic acid. So, in complexometric titration involves formation of stable and water-soluble complexes between metal ions and complexing agents. So, they are widely used for the hardness determination and estimation of metal containing pharmaceuticals. So, in this, metal and ligand complex formation takes place, and so use of stable chelating agents used as a titrant, that means EDTA, and pH is very important. Controlled pH conditions only the stable metal ligand complex formation takes place, and metal ion indicators used for color change, and 1:1 is stoichiometric reactions takes place. In complexometry, what is use of chelating agent? So, chelating agents also called as ligands. Ligands means is the electrons donating groups. The most common ligands in EDTA which can bind metal ion through 6 donor sites, so making its hexadentate ligand. This forms a very stable chelate complex. And use of metal ion indicator is also called as PM indicator. A metal ion indicator forms a weakly colored complex with metal. At the end point, EDTA displays the indicator from the metal complex and it produces sharp color change is observed. And in example of metal indicators or PM indicators are eriochrome black tea for magnesiums and calcium titrations. So also it is called as solochrome black 2. And what is use of pH? So metal EDTA complex formation is pH dependent. Thus, titrations are carried out in specific buffer solutions. So, specifically the optimum pH is pH 10 for calcium and magnesium, pH 5 for ferric ions, and pH 1 to 2 for heavy metals. And buffering ensures maximum complex stability and clear endpoint direction. So, the buffer is used to maintain this pH. And in direction of endpoint, at the endpoint, all metal ions are complexed with EDTA. The indicator gets released and changing color into wine red color. And all metal ion form complex with the indicator. At the endpoint, the indicator released and it form complex with the EDTA to produce the color change from wine red to blue color. Complexometric titrations are primarily based on, so option C, formation of stable metal and ligand complexes. EDTA reacts with metal ions in which stoichiometric ratio. So 1:1, option C. Maximum complex stability occurs at, so option A, alkaline pH, that means pH optimum, pH is 10 for calcium and magnesium metals. Next, complexometric titrations we will discuss about. We have to discuss chelating agent, sequestering agent. So chelating agent chelating agents are multi-dentate ligands that bind to a metal ion through two or more donor atoms, and forming a stable ring structure, like it is also called chelates. And sequestering agents are substances that bind metal ions to form stable and water soluble complexes, thereby preventing them from participating in unwanted reactions. And examples of chelating agent: oxalate, EDTA. So oxalate is an example of the bidentate ligand, and EDTA is a hexadentate ligand. And sequestering agent examples also EDTA. So it form complex with the calcium magnesium ions and the ferric and zinc ions, zinc metal atoms. And citrate is a type of sequestering agent. So it form complex with the calcium and magnesium metals. And EDTA is most preferably used. So it is strongest and most widely used chelating and sequestering agent. Which of the following is a chelating agent? So option C, oxalate. Primary function of sequestering agent is, so option B, bind metal ions to prevent undesirable reactions. The strongest sequestering agent commonly used is, so option A, EDTA. Which is not a chelating agent? So option C, Cn minus ion. In complexometric titration, Werner coordination number. What is Werner's coordination number? Werner proposed that metal ions in coordination compound possess two kinds of value. So one is a primary valency, two kinds of valency. First one is a primary valency, it is type of oxidation state, and secondary valency, it is type of coordination number. And Werner's coordination number refers to the total number of ligands, donor atoms, directly bonded to the central metal ion. For EDTA, diethylene diamine tetraacetic acid, EDTA is a hexadentate ligand. It can attach to the metal atom through 6 donor atoms. For example, 2 nitrogen atoms and 4 oxygen atoms. Therefore, EDTA binds to a metal. The coordination number provided by EDTA is 6. In a metal EDTA complex, such as metal EDTA complex, EDTA ligand occupies 6 coordination sites. The EDTA is the strongest and widely used chelating and sequestering agent. So this is the complex formation between EDTA and metal atom. So metal atoms occupies the central metal and surrounded by the 2 nitrogen group and 4 oxygen groups. So there are 6 coordination number. According to Werner, coordination number refers to, so option B, number of secondary valencies. The most common coordination numbers for transition metals are, so option C, 4 and 8. The coordination numbers of EDTA when bound to a metal ion is, so option D, 6. Next, we'll discuss about the classification of complexometric titration. So in classification, there are direct titration, back titration, replacement titration, and indirect titration, alkylimetric titration. So there are 5 types. So direct titration means the metal ion directly titrated with EDTA. So, for example, in determination of hardness of water, and also magnesium ions are directly titrated with EDTA. So, it's coming under the direct titration. On back titration, excess of EDTA is added, remaining EDTA titrated with metal solution. So, for example, aluminum hydroxide gel, alum, aluminum hydroxide, aluminum is a metal atom, is titrated using back titration. Determined using back titration. And replacement titration, metal displaces magnesium from magnesium EDTA complex and it released magnesium titrated. So, replacement titration means mainly calcium, cadmium, mercury titrated, especially calcium gluconate. Calcium ions are estimated using replacement titration. So, the reason is calciums will poorly react with this indicator. So, calciums will react with the indicator very strongly and it forms stable complex so that it is very difficult to react with the EDTA for the estimation. So that we'll add the one more ion of the magnesium, magnesium ion, metal ion. So the magnesium metal ion react with the indicator and when the titrations EDTA first is react with the magnesium and then it is released for the titration. Indirect titration, metal is precipitated and dissolved and titrated. So sulfate estimation via barium sulfate route. And alkalimetric titration, when polyvalent ion is added to a complex and proton is liberated. This acidity and titrated with alkali unbuffered solution, acid base indicator used instead of PM indicator. So you take the screenshot, is a very important for the MCQs because this type of titration which metals are titrated. So direct titration means magnesium sulfate, back titration aluminum ions, and replacement titrations are calcium gluconate. Calcium is very important. Replacement titration is done, and indirect titration is a sulfate estimation. So next, complexometric titration, direct titration is applicable when option B, metal forms stable complex without interference. Complexometric titration, back titration is used when option B, reaction between EDTA and metal is slow. Complexometric titration and replacement titration involves option B, metal displacing another metal from its EDTA complex. And what is metal ion indicator? It's a PM indicator. So example for PM indicator, modern black 2, eriochrome black tea or solochrome black tea. So another name of the modern black is solochrome black tea. And xylenol orange. Muraxide is a ammonium perpurate and chalcone mixture. And finally solochrome dark blue. So these are all the examples of indicator. And in this solochrome black tea, indicator blue in pH 10 and on complex with metal ion pink colored formed and pH 6.5 6.3 and above pH 11.5 reddish in color. So cannot be used oxidizing agent or reducing agents. In acidic yellow, in alkaline is a red. Estimation of aluminum hydroxide gel and zinc and titanium dioxide. So estimation of, it is used for the estimation of calcium in the presence of magnesium. So chalcone mixture is used for the estimation of calcium carbonate and calcium chloride. Which indicator shows a blue color in pH 10? Buffer or forms a pink complex with metal ions such as calcium and magnesium. So option C, eriochrome black tea. Xylenol orange shows which color change when shifting from acidic to alkaline medium. So option B, yellow to red color. Murexide is primarily used for the estimation of which ion? Option B, calcium ion. Which indicator cannot be used with oxidizing or reducing ions? So option C, eriochrome black tea. Chalcone is mainly used for the estimation of chalcones, also called as solochrome dark blue. So answer is option A, calcium carbonate and calcium chloride. In calcium and magnesium titration using eriochrome black tea and EDTA, what is the correct color change at the end point? It's option C, wine red to blue color. Which of the following is true regarding the working principle of complexometric indicator? So option C, before the endpoint, metal ion bind to the indicator and forming a color complex. Next, it is very important topic under the complexometric titration is masking and demasking reagent. So masking agent means, so it is example is masking agent. The some when we want to estimate more than one metal atoms, more than one or two metal atoms to all together. In that case, so all the metal atoms will react same together with the EDTA. So that shows error report. In order to prevent that one, we are adding masking agent. So we are titrating one by one. So this masking and demasking especially used when we want to estimate more than one or two metal atoms. So one or two metal atoms are there. First we will using masking agent, we will mask two atoms and we allow only one atom to for the titrations react with the EDTA. Then again we will add demasking agent, we release the one atom and we will do the titration with EDTA. And again we will add demasking agent and we will do the another three. So like that we will take two or three readings for separately for each metal atoms. So for example, precipitant, that means when we are adding the masking agent, it will precipitate the other ions. For example, sodium sulfide and thioacetamide. So it will mask or precipitate the copper and cobalt and lead. So along with this, suppose aluminum is there. If we want to estimate the aluminum, so these metals may interfere. So in order to remove this interference, we will add this masking agent to precipitate the copper, cobalt, lead, and only aluminum will react with the EDTA. So next is the sulfate. Sulfate is to mask the lead and barium. Oxalate also lead and calcium. And fluorides are lead, calcium, and magnesium. And ferrocyanide is zinc, copper. And cupron, cupferon, and 8-hydroxyquinol is used for heavy metals. So to mask or precipitate these ions, we'll use these precipitant. So then only these ions, suppose if it is present during the metal ion estimation, will not interfere. And complexing agent. Complexing agent, so triethanolamine. Complexing agent, triethanolamine is used for the aluminum and iron. And for masking, potassium iodide for mercury. And ascorbic acid plus ferrocyanide is ferric. And ammonium fluoride, aluminum, iron, titanium. And dimer capryl alkaline, mercury. So these are all the agent. It is formed the complexing with this metal atom, so that will not interfere in the titration. So these are all the example for the precipitate. It convert the copper, cobalt into the precipitate form. But these complexing agent form complex with this metal atoms. And demasking agent. So demasking agent. So after the, for example, I told is aluminum, iron, and iron along with any other. If a calcium is there means, So first we'll add the masking of triethanolamine. The aluminum and iron both will get masked. Then will only the calcium will react with EDTA and we'll get endpoint. So after that we'll add the demasking agent, release these ions from the masking nature. So this ion again will titrated with EDTA and will take endpoint. So releasing the masked ion from its masking nature. So it is called demasking agent. For example, formaldehyde release zinc from cyanide complex. Acetone is a unmasked calcium by precipitating calcium, and chloroacetic acid breaks citrate complex. So these are all the examples for demasking agent. Which masking agent precipitate copper, cobalt, lead during complexometric titration? So option B, sodium sulfide. Oxalate is used as a masking agent for which pair of metal ions? So option A, lead and calcium. Potassium cyanide in alkaline solution mask which group of metal ions? So option B, silver, mercury and copper. Which masking agent is used specifically for aluminum and iron by forming stable complexes? So option A, triethanolamine. Which masking agent is used to release zinc from its cyanide complex? So option C, formaldehyde. Acetone is used as a demasking agent in EDTA titration because it, so option C, precipitate calcium and free magnesium ions. In complexometric titration, preparation and standardization of disodium EDTA. So preparation and standardization. So preparation will occur molar solution of EDTA we used to prepare. So for 0.01 molarity, we have to take 3.72 gram of EDTA and dissolve in 1 liter of water and transfer to a volumetric flask and make up to the mark with the distilled water and stored in polyethylene bottles. Prevent from the light. So next is standardization. So for standardization of this, magnesium sulfate is used as a primary standard, or zinc solutions also used as a primary standard. So first of all, measured volume of a magnesium sulfate taken in a conical flask, and we will add ammonium chloride buffer at pH 10 in order to maintain pH 10, and we will add the indicator areochrome black tea and titrate with the EDTA till wine red color, it's not a pink, wine red color change to blue color at the end point. Calculate molarity using molarity formula. Preparation and standardization of EDTA. So EDTA ionized in 4 stage due to presence of 4 COOH group. And preparations, so you have to see the molarity formula and you read it this. Best primary standard for EDTA standardization. So option C, standard magnesium sulfate and zinc solution. Buffer used to adjust pH during EDTA titration of calcium and magnesium. So option C, ammonium chloride buffer. Indicator used in EDTA standardization with magnesium sulfate. So option B, areochrome black tea. And estimation of calcium gluconate is an example of complexometric titration. It's very, very important. They are asking from various exams as MCQs and important 5 marks question also. So principle, calcium gluconate containing calcium ion form complex with EDTA. So EDTA is used as a strong chelating agent, and modern black 2 does not show soft color change with the calcium. So therefore calcium is not titrated directly with the EDTA. So displacement titration or replacement titration is used using 0.05 m magnesium sulfate solution is added as a displacing agent. And in mechanism of displacement, first we'll take magnesium solution into conical flask. In conical flask, so there is the calcium ion and magnesium ion. So calcium will add indicator also. So calcium will not react with the indicator because the calcium's indicator, when this indicator initially it should react with the metal ion, it form wine red color. So that wine red color changed to blue color. This is our end point. So when we are using the calcium indicator complex will not formed. So that we are adding the magnesium ion. So the magnesiums and indicator form a complex. So this makes the solution wine red. So wine red, that means color change. So during the end point, first all calciums react with the EDTA. So after the completion of the EDTA, and magnesium really get released from this indicator complex and react with the EDTA. And you will, this wine red color reason is magnesium and indicator complex. So all magnesium get released from the indicator and react with EDTA, and finally there is no magnesium and indicator complex. So the solution change the color from wine red to blue color. So this is the complexometric titration. So stability order of complex, first calcium EDTA forms strong complex, then magnesium EDTA, then magnesium indicator, then calcium indicator. So calcium indicator is very poorly complex, so that it not produce wine red color change. That's why we are using calcium ion, magnesium ion as a replacement ion in order to produce the wine red color of the solution. So the complex between metal, magnesium and indicator produce wine red color. Estimation of calcium gluconate, we need to know. You read it before titration. So magnesium indicator complex form wine red color, and during the titration calcium EDTA form more stable complex. So after the calcium ions reaction is completed and the EDTA complex EDTA complexes it abstract, that means abstract magnesium ion from the indicator. That means indicator start to release the magnesium ion, then this magnesium ion react with the EDTA. And at the end point, magnesium indicator complexes breaks. So all magnesium indicator complexes break, then free indicators alone. So that free indicator color is blue red color at the end point. Ammonium buffer maintains a pH 10. Is the optimum pH is used for the EDTA complex formation. And why is calcium not titrated directly with EDTA using modern blood 2 in the assay of calcium gluconate? So option C, indicator does not show a sharp color change with calcium ion. What is the role of magnesium sulfate in the assay of calcium gluconate? So option C, to displace calcium from indicator and form magnesium indicator complex. Which of the following correctly represent the stability order of complexes involved in the assay? So option C is the correct answer. What is the color change observed at the end point in the assay of calcium gluconate using displacement titration? Option B, wine red to blue color. What is the main purpose of maintaining the solution at pH 10 during complexometric assay of calcium gluconate? So answer in the comment box. So join in our WhatsApp community. You will get hands-on material. Thank you. Like, subscribe and share.